California Highway 120 geology. California Highway 120 runs from Interstate 5 in the Central Valley through Manteca, Oakdale, Chinese Camp, Groveland, and Yosemite National Park. At Crane Flat, it branches off from Big Oak Flat Road and heads for Tioga Pass. There, at the crest of the Sierra, it leaves the park and heads down steep Lee Vining Canyon, past a glacial moraine into the town of Lee Vining. There it joins US 395 and jogs south a few miles before turning east towards Nevada. It ends at the town of Benton, where it intersects US Highway 6. During its journey, it passes through the Great Valley, the Sierra foothills, including the Mother Lode, up the forested western slope of the Sierra Nevada into Yosemite National Park. It passes through granite landscapes, descends a steep canyon past a glacial moraine, an alkali lake, extinct volcanoes, and a hot spring. The geology underfoot is complex and diverse, and probably includes every rock type known to geology. In order to explain this complexity, we need to go back into the early history of the Earth. When the Earth was formed over 4.5 billion years ago, it was a hot ball of molten rock. As it cooled, heavier material settled towards the center, and the surface of the globe hardened. The center of the Earth has a solid iron core surrounded by a layer of liquid iron. On top of this is a layer of viscous rock called the mantle. On top of the mantle rides the crust. The continental plates move around a lot. Sometimes they all come together, and then convection causes them to pull apart again. The last time they were all together, they formed the supercontinent Pangaea. About 288 million years ago, Pangaea began to break up. California was on the North American plate, which was moving west because the Atlantic Ridge had formed in the middle of Pangaea and was splitting it apart. The North American plate was overriding an oceanic plate called the Farallon Plate. It in turn was being driven eastward by another plate, the Pacific Plate. At that time, California ended somewhere in the present-day Utah. About that time, an island arc was mashed onto the west coast, extending the continent to the west. As the Farallon Plate dived under North America, it created an oceanic trench where debris from erosion and parts of the underside of the continental plate accumulated. As the plate dived deeper, magma chambers of molten granite formed in the mantle and began to uplift the continental crust. Later, when this magma cooled, it became the granite batholiths that formed the modern Sierra Nevada. The uplift formed the ancient Nevada mountains. By 50 million years ago, the Nevada mountains had eroded down to low hills with rivers full of gold-rich gravels. About 25 million years ago, the Farallon Plate had almost completely been subducted under the North American Plate, and the Pacific Plate hit the North American Plate. The Pacific Plate was moving northwest. The forces created the San Andreas Fault. About 5 million years ago, there was a widespread volcanism in the western part of North America. Other forces were also acting on the North American Plate, which caused the crust under Nevada to thin and extend, causing basin and range type faulting. The Sierra formed a huge fault block which was uplifted and tilted towards the west, resulting in a steep eastern slope and a gradual western slope. During the Ice Ages, the Sierra was covered with glaciers, which carved the landscape of present-day Yosemite Park. Traveling east on California Highway 120 is like traveling back in time, geologically speaking. Beneath the pavement, to a depth of many thousands of feet, are layers of sediments going back in time to 65 million years ago, the Mesozoic Age, when the Farallon Plate began diving under the North American continent. The Great Valley was filled with sediments from the early Nevada volcanic mountains, which were eroding away into the Foreark Basin, which became the valley. This process continued in different forms up to the present day. The younger layers are sand and gravel called alluvium, which overlay older layers of sandstone and shale. The first prominent feature you see is Lover's Leap just outside Oakdale, overlooking the Stanislaus River. This hilltop with an American flag planted on its top is a remnant of volcanic mudflows from volcanoes near Sonora Pass. These mudflows, mixed with layers of volcanic ash, were caused when the ash mixed with snow and water. The resulting rock is known as the Mertens Formation. Further up, past Knight's Ferry, the road becomes a divided highway. Large boulders can be seen in places alongside the road. These are volcanic bombs formed when chunks of viscous molten lava became airborne from those volcanoes up by Sonora Pass and landed here. Lava from these volcanoes flowed into the valley of the ancient Stanislaus River and hardened. Over time, the surrounding country rock eroded away, leaving these inverted valleys. Beneath them, accessible in some places, is gold-bearing gravel. The best example of this is Table Mountain at the junction of highways 120 and 108. Just past the junction is the community of Chinese Camp. At Chinese Camp, Red Hills Road heads west to the Red Hills Recreation Management Area. This area contains serpentine and dunite, which are ultramafic rocks which have been intruded from the upper mantle. Ultramafic rocks contain a lot of iron and magnesium and are very heavy if you pick them up. The surrounding soil is very red, the result of oxidized iron. This area is part of the Bear Creek Fault Zone. This fault is a deep thrust fault that extends deep into the crust and was the probable path of these ultramafic rocks. Further west, Red Hills Road terminates into County Road J59. Along J59, also along US 49, between highways 108 and 120, you can see peculiar rocks sticking out of the ground. These are the so-called tombstone rocks of the Mariposa Formation. They are part of a slate layer that has been folded so that they are vertical. Past Chinese Camp and up Priest Grade is mostly a metamorphosed sedimentary rock with occasional quartz veins. At the top of Priest Grade is the town of Big Oak Flat, which is in the middle of the Mother Lode. There are veins of quartz here, one that is hundreds of feet wide, just off Black Road. This is where the hard rock 49er miners found their gold. The Mother Lode is only 6.5 miles wide, but extends 70 miles from Mariposa up into Amador County. Up country past Buck Meadows, you come to the rim of the world. Looking north, you see the steep canyon of the Tuolumne River. The canyon, which is 2,000 feet deep, is the result of the recent uplift of the Sierra Nevada, causing rapid erosion. This is in sharp contrast to the valley of the South Fork of the Tuolumne, which is much shallower due to slower erosion. The South Fork starts to deepen just after the highway bridge next to Rainbow Pool and then drops about 1,400 feet into the main Tuolumne Canyon. Past the bridge is the turnoff to Cherry Creek Cherry Lake Road. If you drive up this road past the bridge and up the hill, you will see white boulders on the hillside to the left of the road. These are called core stones. They are granite boulders that have formed in place from weathering as opposed to erosion. What happens is that water penetrates cracks in the granite and over time dissolves that part of the rock, resulting in round boulders. Just before the entrance to Yosemite Park is Evergreen Road, which leads to Hetch Hetchy Reservoir. The reservoir fills Hetch Hetchy Valley, a little brother geologically speaking to the Yosemite Valley. It supplies water to the city of San Francisco. The dam was completed in 1923 over the objections of legendary environmentalist John Muir. Hetch Hetchy Valley is U-shaped, the result of glaciers scouring out and reshaping the original V-shaped valley of the Tuolumne Valley. Likewise, the Yosemite Valley was formed by the glacial reforming of the Merced River Valley. 7.5 miles past Big Oak Flat entrance to Yosemite Park, Highway 120 branches off from Big Oak Flat Road and becomes Tioga Road. Following Big Oak Flat Road another 10 miles, it drops down into the Yosemite Valley and joins up with El Portal Road, which is California Highway 140. As you enter Yosemite Valley, the first thing of interest on the right is Bridal Veil Falls. This is a classic example of a hanging valley. The gently sloping Bridal Veil Valley was truncated by the glacier flowing down the Merced River course, resulting in a steep drop, hence the falls. Another example of a hanging valley is Yosemite Falls, which actually consists of 3 successive falls with a total drop of 2,425 feet. On the left is the towering wall of El Capitan. It is composed of white granite, composed mostly of quartz and white feldspars. At the end of the valley is Half Dome, which is composed of granodiorite, a variety of granite which has more of the darker minerals hornblende and biotite. Most of the rocks in Yosemite Valley, in Yosemite Park, are granite. Granite is a mixture of several different minerals, primarily feldspar, quartz, and some darker minerals such as biotite and hornblende. The Sierra batholith, which Yosemite is part of, was formed in stages, with various magma plumes crystallizing out at different times under different physical conditions. The chemical composition varied over time, hence the different types of granite in the park. The 3 main types are called granite, granodiorite, and diorite. Diorite is the darker because it has more biotite. A good place to view El Capitan granite is in the Cookie Cliff rock slide. The white granite has dark inclusions of diorite, which the fluid magma did not fully dissolve. To get there, at the junction of highways 120 and 140, turn west on Highway 140 and travel west about 6 miles. One of the best places to see Cunacrest granodiorite is up close in the Glacial Point parking lot. To get there, take Wawona Road, which is Highway 41, south for 9 miles and turn onto Glacier Point Road. Travel 19 miles to the Glacier Point parking lot. There are fresh exposures of Cunacrest granodiorite there. This granodiorite is darker than the Half Dome granodiorite. Looking east from Glacier Point, you can see Half Dome edge on. Most of the rock you see is from one intrusion called the Tuolumne Intrusion, which occurred about 100 million years ago. These rocks are composed of Half Dome granodiorite. Also visible are Vernal and Nevada Falls. These are not hanging valleys like Bridal Veil or Yosemite Falls. The topography forms giant steps. The cause of these steep cliffs is still under study. The glacial U-shape of Yosemite Valley is quite apparent from this viewpoint. Backtracking to the Tioga Road turnoff at Crane Junction, we proceed 27 miles to where the old Tioga Road turns off. The old road proceeds for about 2 miles to the trailhead to May Lake. The rocks along the trail first seen are half-dome granodiorite with dark diorite inclusions. Further up the trail we come to scattered metamorphic rocks, some rusty red, other gray, which show evidence of compression and folding. The trail to the lake is 1.2 miles with an elevation gain of 500 feet. May Lake is a natural lake formed by a glacier which scoured out a basin in softer metamorphic rocks. On the southwest corner of the lake is a peninsula which is composed of white quartzite. There are gray and black folded veins which have invaded the quartzite. West of the lake towers the granodiorite peak, Mount Hoffman at 10,850 feet. This peak sits in the geographic center of the Yosemite Park and provides a map-like view of the entire park. What are all these metamorphic rocks doing in Yosemite among all the igneous granitic rocks? There are two theories. One is that they were formed on the sandy shoreline of western North America. However, there should have been shale here rather than sandstone that has been metamorphosed. Similar rocks are 200 miles south in the Mojave Desert. These rocks could have been pushed north by tectonic forces along a fault. Alternatively, there could have been kinks in the old shoreline with sand rather than mud that was subsequently compressed and metamorphosed. Next, we continue along Tioga Road to Olmsted Point. The rock there is half-dome granodiorite. Sitting on the top of the smooth but jointed granite sits boulders called glacial erratics. These are boulders that have been carried from elsewhere by glaciers and deposited here. These boulders here are composed of Kuna Crest granodiorite. Just past Olmsted Point, we come to beautiful Tenaya Lake. The interesting thing about Tenaya Lake, from a geologic point of view, is the tree stumps that are poking out of the water. These stumps are dead lodgepole pines that are as much as 50 feet deep. Obviously, lodgepole pines do not grow underwater, so the lake must have been much shallower when they drowned. According to radiocarbon dating, they died around 1300 AD. This seems to suggest that the West was undergoing a great mega-drought, much worse than we are experiencing right now. Traveling east out of Yosemite Park on Highway 120, you enter steep Levining Canyon. During the last ice age, this canyon and adjacent ones were filled with glaciers. At the bottom of the canyon, just before the intersection with US 395, you can see glacial moraines on each side of the highway. Up close, you can see a landscape full of round boulders left behind by the retreating glaciers. There are two episodes of glaciation. The first, the Tahoe glaciation period, peaked around 100,000 years ago. The younger one, the Tioga glaciation period, happened about 20,000 years ago. Once you reach the intersection of Highway 120 and US 395, Mono Lake comes into view. This highly alkaline lake, 3 times as salty as the ocean, is a remnant of a much larger prehistoric lake called Lake Russell. The land east of the Sierra is part of a new geologic province or domain called the Basin and Range Province. Once the Farallon Plate had finished subducting under the North American Plate, the plate behind it, the Pacific Plate, crashed into North America and started moving north. The San Andreas Fault was formed at that time, and a piece of western California started moving with it. However, the rest of the continent was stretched in a northwest by southeast direction. This caused thinning of the crust, further thinning and fracturing the crust. The fracture of normal, that is to say vertical faults, created alternating blocks which rose or fell, creating ranges and valleys known as basins. One of these basins, Mono Basin, filled with melting glacial water, creating Lake Russell. Over time, the lake evaporated to near its present size as Mono Lake. If you travel north about a mile on 395 through the town of Levining, you will come to a turnoff on the right to the Mono Lake Visitor Center. From there, you can get an unobstructed view of 3 volcanoes. That is to say, 2 islands in a peninsula that erupted underwater when the lake was much higher. Negret Island, the small dark island, is not basalt, but dacite, a lava which contains more silica than basalt. The colored island, Paoha, consists of lake sediments overlying a rhyolite dome which pushed up from below. The oldest, Black Point, was formed 13,000 years ago as an underwater basaltic volcano. To reach Black Point, travel 3.5 miles north from the Visitor Center on US 395. Turn on Cemetery Road. The road is paved until you reach the cemetery. Then it becomes a gravel road. Continue for about 0.4 of a mile to where you will come to an extraordinary cut in the road on the right side. What you will see are folded beds of tephra deposited on top of level beds of tephra. The explanation for the folded beds is that they were deposited underwater and then slid down the hard, slippery surface underneath to where they now reside. Next, continue for about 1.5 miles to a fork in the road. Take the right-hand fork and continue 2.5 miles to the end of the road, which is the trailhead for Black Point. To your immediate right is the Black Point Cone, and to your left is the north shore of Mono Lake. One of the interesting features of Black Point are the fissures which are on the west side of the mountain. Climbing through the black volcanic sand is difficult. I was unable to find the fissures after an hour of searching. Later I discovered their location on the satellite map. One of the interesting things about Mono Lake are the tufa towers. These formations are composed of calcium carbonate which precipitated out underwater. The best way to view these is from the south shore of Mono Lake. This can be reached by driving south on US 395 about 5 miles and turning left on California 120. Just before you come to the turnoff for the South Tufa area, a road goes towards Panem Crater, which has a resurgent rhyolitic dome in its center. Panem Crater is 650 years old and is the youngest member of the 18-mile-long Mono Inyo crater chain. Looking south from Panem Crater, you can see 2 more domes. These and Panem Crater are part of a 10-mile chain known as the Mono Craters. These are domes formed when lava filled the original craters. The lava is rich in silica, which formed volcanic glass known as obsidian. The 10-mile-long chain of domes were formed during a period of volcanism that started 35,000 years ago and was active as recently as 600 years ago. We will now take a side excursion south on US 395 to explore more of the volcanic activity in this area. Further south, at the south end of the Mono Craters, is the Obsidian Dome, which isn't a dome, but a lava flow known as a coulee. It can be reached by Glass Flow Road, a dirt road that turns west off US 395. It is about 2 miles to reach a parking area where you can see the dome. Obsidian and rhyolite have the same composition. Obsidian is a glass because the lava cooled too fast to form crystals, while rhyolite cooled more slowly under the surface. Further south, the Inyo craters can be reached off the Mammoth Lake Scenic Loop Road. The craters were formed when underground dikes encountered groundwater, causing an explosion of steam. Both the Obsidian Dome lava flow and the Inyo craters were created during a volcanic episode in the year 1350. Heading south on US 395, turn west on Mammoth Scenic Loop. At the intersection with California 203, head west 0.9 miles to the turnoff to the earthquake fault, which is clearly marked with a sign. Travel north 1/4 mile to the parking lot. There is a short path to the fault. Geologists are not sure if the fault was caused by an earthquake or a fissure caused by crustal stretching as a result of volcanic activity. Trees in the fissure indicate an age of at least 200 years. Devil's Postpile, an interesting geologic feature, can be reached by shuttle from Mammoth Mountain Ski Lodge. The postpile consists of thousands of hexagonal basalt columns as much as 60 feet high. The upper surface is flat, having been ground off by the Tioga Glacier. Another feature is the Long Valley Caldera. Although 395 drives through the center of Long Valley Caldera, it is best viewed from the top of Mammoth Mountain, which is accessible by the gondola at the Mammoth Mountain Ski Lodge. The caldera was formed 767,000 years ago after an underground chamber of magma erupted and blew 150 cubic miles of Bishop Tuff over the entire western United States. 3 miles southeast of the intersection of 395 and California 203, turn north on Hot Creek Hatchery Road and follow it for 3.3 miles to the Hot Creek geologic site. Park in the parking lot. Hot Creek runs through a 200-foot gorge at that point. There's a short path down to the hot springs. Along the way down, you will see chemically altered rhyolite clay. It's now time to return to California Highway 120. Travel east on California Highway 120 past Mono Lake about halfway to Benton, and you will see several interesting rock formations alongside the road. Some are weathered granite that was not covered up by the Bishop Tuff. Also, right across from the road, in some instances, you can actually see the tephra of the Bishop Tuff. 5 miles west of Benton is a settlement of Benton Hot Springs. There are several B&B resorts there which feature exclusive hot springs access for their guests. Thank you for taking this geologic road trip with me. Now I would like to acknowledge my references. First, Geology Underfoot in Yosemite Park by Alan F. Glazner and Greg M. Stack, and Geology Underfoot in Death Valley in Eastern California, second edition by Alan F. Glazner, Arthur Gibbs Sylvester, and Robert P. Sharp. Also, Roadside Geology of Northern and Central California, second edition by David Alt and Donald W. Hindman. All three books are published by Mountain Press Publishing Company. In addition, I included a screenshot of the Google map for Black Point showing the fissures. Thank you.